So I'd like to begin too by acknowledging, of course, that Kwantlen proudly has its name from the Kwantlen First Nation, and that I'm joining you today from the unceded traditional and ancestral lands of the Musqueam, Squamish, and Tsleil-Waututh Nations. I'm, of course, grateful for today and for these lands, and of course, reflecting, especially in the last few weeks with the flooding, about our responsibilities in caring for them during climate crisis. So, of course, if any of you are wanting to acknowledge where you are today, please use the chat to let us know where you're coming from. So I'm delighted, of course, to be hosting today the Arts Speaker Series and to be introducing Byron Peters from the Fine Arts Department. So I'll tell you a little bit about Byron and, of course, the title of his talk. As I mentioned, we will be saving some time at the end for questions. So at that time, you can either raise your hand or type your comment in the chat. And you can always turn on your camera when you're asking Byron the question, just so he can see who you are, and unmute yourself then. As we get started, of course, just tell you a bit about Byron. So Byron Peters is an artist and writer who works with drawing, sculpture, text, sound, installation, and film. His artworks often take the form of long-term collaborations. This collective research has engaged with, for example, the histories of science and mathematics, digital labor, and the effects of gentrification and displacement. His solo and collaborative artworks have been exhibited at the Darling Foundry in Montreal, Parasite in Hong Kong, ICA Miami, the White Building in London, the Elizabeth Foundation for the Arts in New York, the Asian Art Museum of San Francisco, and more locally at venues such as Center A, Vivo, the New Media Gallery, Access, and Arts Speak. With an interest in interdisciplinarity and pedagogy, he has given performative lectures at institutions such as the New School in New York, the Center for the Study of Contemporary Art at UCL, and the Victoria and Albert Museum and the London School of Economics. You've been busy, Byron. And he's currently working on a collaborative film with the activist and community television producer Sid Chow Tan to be released in late 2022. Today, Byron's going to be sharing his work and speaking on his presentation entitled Thought Experiments and Misinventions, Stories of Forming Numbers. So I'll hand it over to you, Byron.
Cool. Thank you very, very much, Shelley. And thank you, everybody, for coming. I really appreciate it. We're getting our first glimpses of sunshine, and here you are. So I'm very grateful. And I'm looking forward to the question period at the end, too, in which we'll get the chance to interact. So, yeah, I'm going to talk for about 40 minutes, and then we'll have about 20 minutes at the end. Let's see here. Just going to share my slides. Alrighty, so I could give a more general artist talk and kind of go through projects and lots of slides about artworks and things like that. But actually today I'm going to take this opportunity to talk about one interest of mine and one ongoing project of mine, which is in and around the field of mathematics. But more generally, thank you, Shelley, for the generous intro. I do work in a lot of different mediums, and a lot of the time my works involve long-term collaborations, as it said. So that might mean, say, working with an architecture firm, or that might mean collaborating with, sorry, just some people still coming in here. That might mean working with laborers and digital labor or something like that. It might mean these sort of things that will take many years to resolve. Projects that very rarely would you have at the end, a polished artwork that you could say like, oh, that's a really great object, and that kind of contains it all. But more so, I'm interested in the long-term conversations and things like that. But for today's talk, I put a fairly vague title to give myself room, depending on how I was feeling and what I was going to talk about. But I am going to talk about these things. So the things in the talk are thought experiments and misinventions, so not inventions, but rather things that have been invented wrong, and stories of forming numbers. So numbers that would be the part on mathematics. And I am going to talk about math, but I promise you, as the speaker series is also billed to be for a non-specialist audience, don't worry, I'm not going to blast you with some heavy-duty mathematics. And myself, as a non-specialist, it would be pretty hard for me to do so anyway. But if there are any sorts of things that I say that I go too fast, I look forward to the period at the end, and hopefully we can get to the bottom of it. So I'm going to start here. So these are two films that I made, one in 2017 and one in 2018, and I'm actually going to show little clips from them throughout this talk. The art world, or the contemporary art in general, or cinema might call these films, but actually what they are and what I designed them to be are educational YouTube videos. So they're not, sometimes people are a little bit shocked when they come to a screening or something and it's very informal, the language, because it's not really built to be a tightly refined object, but it's built more to fit into a YouTube algorithm in which there's a certain sense of humor and there's a certain freedom in that. But it also, that place, YouTube as education, interests me a lot because I meet more and more people who are learning vast amounts of things from YouTube, and what gets picked up by the algorithm, of course, becomes more hegemonic in knowledge and things like that. So these are these two films that are loosely about mathematics that I will occasionally in this talk reference back to. One is called Pure Difference, and the other one is called 10 minus 3 equals 13. Before I start talking about math, though, I kind of want to do a little bit of a conceptual intro. So, and I'll tie it to the poster of this talk. So I picked this image because I think that it's a useful tool for giving a general overview of what I'm thinking about in mathematics. So this is a painting by Magritte from 1958, and it's called Clear Ideas. And you have this floating cloud, and you have this floating rock. And Magritte, if you're unfamiliar, he made a lot of what are termed calligrams. And a calligram would be kind of like a diagram for thinking that involves oftentimes text and image, but they're these sorts of like thought objects. This one, called Clear Ideas, you have these two floating things above an ocean. You could say maybe that like the cloud represents the realm of immateriality. So something like the way that we experience the internet that I'm presenting to you on right now. And then you could say maybe the rock represents the material, the concrete side of that. So maybe that represents the mining required, the rare earth minerals that are required for the gadgets we're using. Maybe the rock is the bodies. Oh, got somebody else joining here. Okay. Maybe the rock represents the bodies and the labor required to mine those minerals or something like this. So we could be zooming here from the cloud, which would be this virtual space, and then we would be going to the cobalt mining in the Congo, or the rare earth minerals in Inner Mongolia or something like that. So there's both of these things at once. Now, this is not what this painting means. In fact, I think it's horrible when people say like, this is literally what a painting means, but this is kind of how I'm using it to set up these opposites between two things. So let's move ahead here to another Magritte painting. Very similar, you might notice. We have our two characters. We have the cloud and we have the rock. But this time they seem to be floating above a town. Now this one's called the Battle of Argonne. And again, the cloud and the rock, they could represent immateriality and materiality. Or you could say the cloud represents pure ideas and the rock maybe represents actions or something like that. There's always these, Western culture oftentimes has these kinds of awkward dichotomies between things. And I think this is sort of what Magritte is getting at, in the sense that it's called a battle. And then you have this battle between these two seemingly opposite forms. But you could also imagine in the town of Argonne, down below these floating figures, those ideas are at play. The conflict between virtuality, ephemeral things, and the concrete, those types of differences are actually part of daily life in the town. It's kind of a metaphor. Now, one step further, the Battle of Argonne was an actual battle in World War I. And in this battle, the soldiers from different sides were both firing into a very thick underbrush. There was no ability to see the enemy. And so what this battle was famous for was just constant firing of weapons without ever aiming. So this kind of sets up an interesting situation here where we have these two opposite forms, and then we have this thing where soldiers are firing into the abyss, a kind of like a fear of the unknown or something like this. If you fear it, you just, whatever, just shoot. So this painting, I think, holds a lot of metaphorical ideas that I'm just delivering right here very generally before I start talking about math, because I want to kind of lead us in to some of the things that come up in mathematics. And definitely, as I'll talk about a bit more, this idea of the differences between the cloud and the rock are very much a part of math. So I borrowed this slide from a thinker that you may know, Donna Haraway, and I think that it's useful also as part of my general intro here to frame mathematics in this sense. So what it says here is, it matters what thoughts think thoughts. It matters what knowledges know knowledges. It matters what relations relate relations. And it matters what worlds world worlds. And lastly, it matters what stories stories. So she's obviously quite liberal with using words that are not normally verbs here, to turning them into verbs. How do you world? You can world. But the reason I'm saying this is just basically it's saying that ideas come from somewhere. So if our society tells itself a certain idea about itself and kind of how it should be run, we will inevitably create stories from that story. And I think this is very important and very fascinating when thinking about mathematics, especially in terms of the claims of math being like a universal language or something like that. What are the stories that underpin the language of math? So this is why this slide is useful for me here. To remember the context, and to also remember, I guess, that art can be a fascinating place where one can imagine other stories. One can imagine then the stories that might come out of a world that tells itself that story. And that's one of the things that I love about art, is that it is this kind of this free zone for imagination around things like that. In this case, though, I'm going to be talking about it in relationship to math. So let's get into it. Sorry for the stock photo here. I always find these types of images to be quite funny in the sense that they usually don't make any sense. I think there's lots of websites about math in movies and how it's the aesthetics of math, it's not actual math. And they're also interesting because of the way that we see mathematics. So this heavy use of symbol, I would say, is kind of an interesting depiction of math because it hasn't been around for that long. For example, here, I think this is from 1489, and this is actually the first time that the plus and minus symbol were used. And the 1489 is still a long time ago. But more interestingly, modern notation as we know it really didn't start in mathematics, this kind of crazy stuff, didn't really start until about the 18th century. So I find these images to be very interesting, and also to remember that mathematics has not always been this way, and that through most of human history, it has been written in the way that I'm talking to you now, in terms of argumentation, or without all of these shorthand forms of being able to do things so efficiently. So that's something that I like to think about, that's actually a fairly recent thing in human history. But I'm also showing this stock photo because I wanted to put something while I explain to you how I began thinking about math at all. So basically, when I was quite a while ago, when I studied at UBC, and I studied some math at UBC, but most of the time I was doing drawing and painting, and but I took mathematics courses there, and I almost got a math degree, but I ended up just focusing on art and kind of leaving it there. And then I thought, well, that was great. I was mostly interested in like abstract concepts and things like this, like counting infinity and things that they start to teach you, at least at an introductory level. But I just kind of left it there, and I never thought that I would ever do math again, until it was about, I guess, 6 or 7 years later. I was living in California, and I was loosely involved with the prisoner hunger strike solidarity group, and just going to actions and things like this. There were a bunch of really, really terrible things going on in terms of institutions like Pelican Bay. In the security housing units, there was a while there where they had actually banned books as a health and safety issue, and also the general setup, of course, of the prison system is brutally racist. And there were at this time, some amazing actions going on, some hunger strike actions. And one of the things that was asked for actually was art and mathematics teachers, art and mathematics tutors. And there were plenty of art teachers. Everyone wanted to be like, I want to be an art teacher. But they had a hard time finding people to be math tutors and math teachers. So that's actually, in that context, that's when I was like, well, I could do that. So I started to work in the field of mathematics in this case, via letter writing, because I was working with people in long-term solitary confinement or security housing units. And so the mathematics lessons would be these very, very long letters, and usually one letter once a month. And of course, in this context, because we're not really allowed to talk about a lot of things, what I started to think about was, what can math communicate? What are the politics of math? For example, like, what's the relationship between mathematics and abolitionism would be a very interesting question, and things like this. So I just starting to think about these things and getting interested in math again. And then actually, let's zoom it. I'm kind of zooming through time here. In a few more years, I actually end up moving to England, and so I'm living in London, and I'm doing some art things like this, but then also I'm feeling a little bit disconnected from the city, and I feel like I need a real job. I'm kind of tired of the art world, and so I see a posting for an educator position at a high school, and I end up doing this for about a year, and this is Swanley School in Whitechapel in Tower Hamlets in London, and I end up working full-time as a math educator. And in this context, I have a lot of time to start thinking about, what is math? And I start meeting more people who think about it, because of course I'm in the math department now. And I start encountering some things that really start to expand my thinking. So one of the things that we're all familiar with is, in a math class, a student will often ask why, and then the teacher will inevitably have to say, well, you have to memorize this and this and this, and then you get a good grade on the test. But I found the question why to be very, very, very useful in terms of my thinking, not only about math, but about kind of our human knowledge production in general, because math is one of these strange zones which seems to have kind of tried to forget its history and doesn't really teach its history next to the equations. And so I started that when something is hidden, it usually means that it's usually begging to be looked up. So I started doing quite a bit more research about the history of mathematics and other, interesting parts about it. So for example, I even started reading the mathematical manuscripts of Karl Marx, who after writing Capital turned his interest to calculus. And one of the things that I noticed in reading his math is that you can actually feel the politics in the math. And you're not supposed to feel that, right? Like math is supposed to be this neutral language, but his rigor that he was trying his attention to calculus was that he wasn't satisfied with how scientific it was. And he tried to make it stronger in line with his view of the most rational thing for the world would be the uprising of the working class. And he had this very kind of pro-science, pro-rational outlook that was connected to politics, but also went into mathematics. And you can feel the ideas in the math in the work on calculus. So that was starting to make me think quite a bit. And I also started to hear the term queer mathematics for the first time, which is something that really interests me in the sense of, I guess you could say, in queer theory, the swerving of a word or the misuse of a word, the reuse of a word for other purposes. There can be swerving of mathematical functions. And this was kind of blowing my mind. Like, really, is this just nonsense, or is this real? Like, what would this mean? And since this time, I've learned a lot that there's actually quite a bit of work on queer computing, and in terms of like Karen Barad's work on quantum physics and queering quantum physics, or queer performativity at the quantum level and things like this. So I'm starting to get interested in how math could potentially be something a lot more complicated than I originally thought. And this is what I'm thinking about in my office at this high school in between classes. And I'm just going to say one more thing about that I learned from this time, and that was I met this man called Leslie Scaife. And he was a teacher there, but he had recently been part of a research group in South Africa. And in post-apartheid South Africa, he had created a journal called Anti-Racist Mathematics. And in this journal, they were basically trying to lay out the future for math, or think about the future of math without white supremacy. So what tools, like what sorts of priorities in society are baked into the math and we should get rid of, for example, is what he's thinking, or versus what kind of tools do we need for the future? What kind of mathematics do we need moving forward? And so he was addressing this term anti-racist mathematics. And again, I'm wondering, like, how could mathematics be anti-racist? It's just this tool, right? But apparently this term actually has been around for some time. So for example, here I'll play a short video. This is actually an intro to one of the YouTube educational videos that I mentioned at the beginning. And this is from, this would be from 1987.
Too often, our children don't get the education they need, the education they deserve. And in the inner cities, where youngsters must have a decent education if they are to have a better future, that opportunity is all too often snatched from them by hard-left education authorities and extremist teachers. And children who need to be able to count and multiply are learning anti-racist mathematics, whatever that may be.
So I'm not sure how the video, if it's coming through MS Teams, but hopefully you got that with sound and everything. This Margaret Thatcher beginning to express some discomfort with this idea of anti-racist mathematics. But what it did is it opened up for me, again, this question, like, well, what could this concept mean? And I started to encounter it more and more. So I can already tell that I'm going to be running a little bit over time, but I'll try my best to move quickly through these things so we can cover more ground. But one of the ways that anti-racist mathematics could be considered would be through the use of statistics. And say, for example, in education, when a student is learning word problems, the word problems would have different names in the word problems. But even better, education would be oriented around understanding such things such as income inequality and things like this. We can understand the world through statistics. Of course, the problem with a graph is that the stuff that makes up a graph, you only see the line of the graph, but all of the life, all of the human bodies, all of the power dynamics, historical relationships that have gotten statistics to where they are, they're not in the graph. So this is one issue in general, but anti-racist mathematics can absolutely and effectively use math for tools of communication. So one great example of this would be W.E.B. Du Bois' infographics at the turn of the 20th century, in which he is working with, he's collaborating with a wide range of students and alumni in the American South to basically create these infographics that are showing basically using mathematics and infographics as a weapon against white supremacy. And these were shown also at the 1900 World's Fair in Paris. But if you ever want to see some really hard-hitting and very beautiful diagrams at the same time, I would recommend checking these out. But then again, and I'm going to kind of jump here from there to the educational side. So we could use mathematics to do design to infographics for communication. The other thing is oriented around how we understand what it is. So for example, in teaching algebra, we could teach its origins in terms of its original meaning, meaning the setting of a broken bone. And this is, or reunion. And so this is the original book on algebra written by Al-Khwarizmi in the golden age of Baghdad around 830 AD. And this origin point of algebra is very interesting if you were to trace and to say teach the relationship of algebra then to the way that algebra is used today, and kind of the ways that it has been moved through different contexts is a very good way to kind of understand global power as well. It's a good way to understand empire at the same time as it is to learn algebra. Lots of mathematical concepts have very strange histories. For example, zero also has a very, millions of people have written books around zero. So I'm not going to go too much into it, but I'll just mention it quickly that it is definitely a very interesting topic in terms of where it came from. Very quickly, what kind of society can actually imagine the importance of nothingness? And it's interesting that, like, until I think about 1202 or so, there was no zero in Europe. And one could say that there would be a priority of having stuff, a priority of progress, a priority of expansion, but maybe not a priority of nothingness and the beauty of it. Meanwhile, of course, ancient Mayan civilizations had zero, and the oldest unambiguous evidence would be in India in around the 5th century. So it's a very interesting history. The history of nothingness and the history of zero is very, very interesting. One book on Mayan mathematics that I recommend would be Who Counts by Diane M. Nelson, in which she kind of unpacks Mayan mathematics in relationship to contemporary statistics and things like this. So that's just quickly, anti-racist mathematics in education could start beginning to trace these flows of power and flows of ideas a little bit more. All right. So now I'm going to spend, I guess we have about 8 minutes here. It's not a lot. So I'm going to just talk a little bit about inventions. And I'm going to talk about one mathematical invention or misinvention, and then I think we're going to end it there. I was potentially going to do a addition and subtraction exercise with you, but I think that might have to be for another time, or maybe in the question and answer period. But anyway, I'll go through, talk a little bit about inventions here. So these numbers, actually, what we're looking at here, Hindu Arabic numerals, they're relatively recent in terms of us using them. Or what do I mean by that? What I mean by that is these numbers are ancient. These numbers have been around for a very long time, but when they were introduced to Florence by a guy called Fibonacci, they were actually banned because they were too easy to use. They were too populist, and at that point, mathematics was in control of was a kind of a tool of power. And so we could get into the history of these numbers, which is very interesting, but I'm just going to basically play a little clip from the video about the Fibonacci sequence, because I think it'll kind of give you a sense of the video work that the YouTube video that I was talking about.
Speaking of inventions, I want to tell you a bit about the Fibonacci sequence. You might think of it as something like this: a sequence of numbers reflecting nature, or something like that. I'm not saying the mathematics itself isn't something akin to magic, but the real Fibonacci sequence looks a lot more like this. You could say the Fibonacci sequence is actually the sequence of events, appropriation, and attribution of ideas to Fibonacci, to European cultures. It is a sequence of spiraling empire and accumulation, a colonial spiral, vacuuming up ideas. Why was he really famous? Because he traveled the world and took inventions back to Europe.
Okay, so you can tell I'm kind of having a little bit of fun with something which is maybe the least of all fun, which is the history of empire. But for the sake of educational videos on YouTube, I enjoy using forms of humor to get some points across, which is why I like the affordances of that medium. But basically what I'm talking about is how inventions are complicated. So I'm trying to debate whether I'm going to actually talk about these because I'm starting to run a little bit out of time, but I will mention this just because it's too good. I'm just going to talk a little bit about inventions. So this is a Claude glass from the 18th century, and what this is it's a landscape viewing device. And what you should do is, if you want to properly appreciate a landscape using this, is you would hold it up and essentially you put in different colored filters, and then you can see the landscape differently. So in this case, it's a lot like this thing here. Actually, it has a shark skin case actually as well. So it's very much like a phone case. It's a lot like an Instagram filter in the 18th century. And it speaks a lot to our ideas of augmenting reality. Now, this is a bit of an aside, but my point is, I think inventions are very, very fascinating because there are moments where we realize that maybe the new is not new. There are moments where desires or societal desires are revealed, and things like that. So inventions are very, very fascinating, as are mathematical inventions. Inventions are not necessarily produced by an individual. They'll usually be associated with one person. Even in this talk, I'll say so-and-so did this. But sometimes or almost every time, inventions come from a collective consciousness. They come from life experiences with many, many people. Even me talking to you right now as an individual is in a way a collective experience because you are here, but also all of the people who have influenced me are coming out of my mouth, essentially. In math, it's not so different, right? This is an example of the Bourbaki group, and they published actually under the name Nicholas Bourbaki, but they were You can see down there, there's a little meme of these people sitting around like smoking and drinking and talking about math. But because they couldn't be recognized as a collective, they just called themselves Nicholas. And still today, those books are some of the more foundational texts on analysis in mathematics. So my point here is that inventions are always collaborative, collective in a sense, even when they're claimed by an individual. Okay, so I'm going to end with a story of a misinvention, because it's in the title and I feel like I should deliver on my promises. So a misinvention would be something that doesn't really fit in with its time, right? Like it doesn't quite, maybe it's not seen to work, or it doesn't quite do what it says on the box, or a misinvention, like an invention though, can oftentimes show a lot about the world. So in math, a misinvention, these are kind of like misinventions. On the left-hand side here, we have the equation for the perfect handshake, which was actually sponsored by Chevrolet. And on the right side, we have the equation for Blue Monday, which is supposed to be the saddest day of the year. But both of these are a little bit suspect. The saddest day of the year was actually a promotional campaign by a travel agency where they got a whole bunch of academics to write peer-reviewed papers on the saddest day of the year. I wouldn't say that these equations necessarily work. Or we could go deeper and we could get into financial algorithms and things like this and start to talk about usages of mathematics and misinventions. This is the Black-Scholes algorithm. But what I want to say, and with my last example here, is not this type of misinvention. The handshake, the worst day of the year, these types of things. The math that they're using actually is still everyday math that is built from the accepted foundations of mathematics. But what I'm interested in with misinventions is when the fundamental things about the language itself are invented or not invented, or invented wrong. So the thing that I'm going to end on here is a short lesson on negative numbers and the misinvention of negative numbers. All right. So negative numbers, again, I'm going to refer to European history here. There's been some very I don't know. I would say that people in the history of negative numbers were kind of filled with a lot of fear. You could say there's a quote from Francis Maceras in the late 18th century, and he says that the negative numbers darken the whole doctrines of the equations and make dark of the things that in their nature are excessively obvious and simple. And I think his use of darken is loaded, and there's a whole bunch of kind of complicated things in that. All I'm saying is that people were afraid of negative numbers because they're less than stuff. Like, what is that? And meanwhile, negative numbers had been around for a long time in daily use. For example, the concept of debt. But I'm going to give you a very quick demonstration of the first time that negative numbers were misinvented by this guy. His name is John Wallis. In the early 17th century. So if we have a circle, we have one piece in the circle. The circle is one piece. And if you cut it into half, you have two pieces. So half, two pieces. If you cut it into three pieces, 1/3, if you cut it into thirds, you'll have three pieces. If you cut it into 1/5, you'll have 5 pieces. Cut it into 1/20, you get 20 pieces. So basically what we're doing here is we're just getting more pieces from making smaller parts. And you can go on and on and on like this. This is what Wallis is thinking. This is before negative numbers. So you get a very small fraction, and you would get many pieces. Now, this is where it gets kind of weird, because if you can get a fraction that's going to be very, very, very small, you could actually get an infinity of pieces. Close to it. It's another conversation whether or not it's actually infinity. But you can get a lot of stuff by making things very small. So the question then would be, what is a negative number? And this guy back then is like, wow, what is this? It's terrifying. Like, what could be less than something? And mind you, also at this time, there's no direction of the number line or anything like this. So numbers are floating around and they're just scary, this negative something. So if we're splitting it into tiny little pieces that are almost size 0 and we get a lot of them, this guy Wallace was like, oh, well, if we split this circle into negative pieces, we'll get even more than infinity. Like, we'll get like a super infinity. And he kind of imagined it like this, like negative numbers would explode stuff and basically create more stuff. And I think this is a very interesting example because it shows in mathematics this interesting, maybe this bias or desire for more things. So he was thinking of negative numbers as a tool in a way for like the accumulation of more things for an idea of growth. Of course, later it would just become the number line. We just like control it and put them down there, and we'll just put them below 0 on a straight line. Okay, so rather than kind of spending more time telling more stories of math and taking all of our question and answer period up, I'm just going to leave it there without a tight conclusion. And then maybe a few more general thoughts can come out in the question and answer period, rather than me kind of spelling out some of my conclusions I've come to. Thank you very much for listening, by the way.
Thanks so much, Byron, for that fascinating talk. And I had no idea you had this rich kind of mathematical interest, which is amazing. So thank you so much for that and sharing. And of course, the floor is open, right, to questions from the audience. So feel free to raise your hand, turn on your camera. Oh, I see a hand already. Greg Simmons, I'll call on you if you wouldn't mind turning on your camera to ask Byron your question, Greg.
Thank you. Thanks, Shelley. Thanks, Byron. That's so interesting. There's so much I want to ask, but I guess I'm kind of thinking like from a philosophical kind of perspective, because you've outlined so many interesting examples of like how math is, it's social, it's political, right? And how all these factors around how it's taught, what kind of examples we use, who gets credit, the preference for individualism, and of course, colonialism and geopolitics and all this stuff. To what extent does that affect? I guess what I'm asking is there still a math? Because the standard representation, the kind of iconic view of math, right, is this kind of Platonic thing that stands outside of history, of society, that points to some kind of truth. Though I know it's not that. I mean, I remember my intro calculus teacher once telling me that like the standard kind of derivation of derivative calculus is BS, and like it really is division by 0, and it's you can prove it, but you need numbers. I don't know. I'm not a mathematician, but. So, like, for instance, with like, is there like I'm rambling on, but is there like a translatability between, say, Mayan math and contemporary math and Western math, let's say, or Arabic math and Western math? Is there something that's universal, or is it kind of like, I'm thinking of like Kuhnian paradigms and the fact that it's very much underdetermined, and we could have maths that are just radically different and don't really translate, but they're equally valid. I know that's a really big question, but it's what I was thinking about when you were presenting all these interesting examples. So I don't know if you have any thoughts on that.
Thank you very much. Yeah, I appreciate those reflections, and I think I won't I actually am not really that qualified to speak at length about the huge question that you're asking. But I am very interested in contemporary, like we're just talking in this talk, I'm talking about, 18th century mathematics or whatever. But I am very interested in some of the things that are being talked about now in terms of the multiplicity of algebras, for example, that are being created. And I think particularly in the field of category theory, which is to put it generally, if you're thinking about two things and they have a relationship, imagine that relationship now with a whole bunch of other relationships. And then now category theory would be the relationships of those relationships. So, and it's kind of looking at math, like it's looking at the history of math and the history of knowledge, and then it's kind of piecing together connections between these things and trying to make some sense, even if they are radically different mathematics. So I think there's a lot of work being done on that. I wish there was a little bit more attention to make it more accessible to the public. I think that's obviously one of the challenges with mathematics. But anyway, thanks.
So kind of a meta math.
Yeah.
But I guess the question is, does that really, stand outside in some absolute way? But anyway, that's really interesting. Thank you. I'll stop there.
Thanks, Greg. Are there any other questions from the audience, either hands or in the chat? Nope, I think I see a hand up. Just trying to see who that is. Just a second. Maybe not. Nope, okay. I was going to ask a question. Oh, maybe Adele. I see Adele. Adele, would you like to ask your question?
Hi. Yes, it's a bit of a sneaky question. Byron, I noticed that you have 87 slides and we only got to see 30 of them. I know we're not going to get to all of it, but can you give us a sense of some of the other things that you were going to venture into, because I'm very intrigued.
Cool, thank you very much. Yeah, actually, I wasn't aware that this platform in particular shows the number of slides that you have. And so what I sometimes do when I'm putting together presentations is I just move the ones that I'm not going to use and I move them to the bottom just in case. And I just didn't delete them. That said, the things that there was about 10 more or 15 more slides that I was going to go through. And what those were about was the complications with adding and subtracting and how that is played out in different societies. So, for example, if I give you something, you would call that subtraction. But if I know you very well and we share, or this is just in a general case, like if a person from their family gives something to a family member, they're not necessarily losing possession of that thing. And yet that's still called subtraction. But in a way, by giving it, you're giving access. So it becomes adding and subtracting at the same time. And there's and this would be called informal mathematics. And there's an interesting history of it in terms of societies with different values around private property developing different mathematics. And so that I was going to kind of do a little bit of things on that. But thank you for inviting me to talk about it.
And I think I see another hand, Mark Vardy.
Yeah, thank you so much. And lots of interesting material to think with and through. I want to go back to the slide you had from Donna Haraway. She's a great thinker. I appreciate her work. And I want to sort of tie that in with the exchange you had with the incarcerated individuals who are in like solitary confinement, I think you said, and through a letter exchange. And I'm just wondering, if we think about, what stories or what words we use to narrate our understandings, what came out of that exchange that you found surprising, or that your audience here on this call might find surprising about how these inmates related to math? or just the opportunity to learn math. And I mean, was there anything that came out of that exchange that you felt was like wouldn't have come out if you were in a classroom setting? Like, was there anything about the exchange of letters and sort of narrating math in that sort of letter form that emerged, that kind of that retold, reshaped the story that you had around math, I guess, or that we might have around math?
It's a great question. Thank you very much for prompting that. Yeah, I definitely think that the context really, and it's sort of why I used it as a way to describe kind of how I've begun to think about math, because in that context and with one individual who I still have an ongoing mathematical relationship with, the question has never been around learning necessarily pragmatic skills in society, sort of how in a high school you'll kind of be taught, they'll tell you you're learning, it's like Math 10 or something, but you're actually learning kind of like economics word problems in many ways. You're not actually really learning what math is. But in the context of letter writing, which is also a very intimate form of communication, and then where the math doesn't actually, the goal of the math is not necessarily to be pragmatic, you can enter into a very interesting conversation about maybe the symbolism of certain things, or metaphor can become important. And also storytelling. I mean, there's actually a long history of mathematics in prison as well, in terms of famous mathematicians being locked up and things like this. And so I think, I mean, maybe the joke that you could make there is that there's some no, actually, I'm not going to go there, but there is a long history of mathematics in prisons. And I think one person that would be interesting to look at, and that I've talked about quite a bit with folks that I've spoken, or that I've been writing letters with, is Évariste Galois, who was a French revolutionary who was in prison before basically coming up with an entire field of mathematics. And his work is very political, as well as presenting quite abstract mathematical concepts. And so sometimes in talking about the history of math a little bit, ideas start to open up a little bit in the field of kind of like numbers and concepts. But yeah, I think maybe the most interesting thing, just to repeat myself, is that to take away the absence of the program that math has to have in order to fit into a particular type of world, and then to kind of imagine, well, what actually gives us pleasure? Like, because we're like, what actually is good for us and think, because problem solving is such a pleasurable thing, or working collaboratively can be such a pleasurable activity. So sort of putting that as the priority versus like, you must learn this to get a job, I think is definitely something that I appreciated out of those exchanges.
Great, thank you very much.
And I see a question in the chat too from Jessica. She said, is there a paper that discusses anti-racism math for dummies and or queer math for beginners? Anything you might be able to recommend, Byron?
I have been looking for these things for years. And I think that it's, yeah, I really wish. I'll have a think about it, and then maybe I'll reach out with some suggestions. But actually, one of the projects that I'm working on now with a brilliant thinker named Sajjit Sumal, who lives in Toronto, is we're trying to, and because we're kind of in and around the field of art, and art is actually quite good with these types of things, because sometimes when I walk into a room of mathematicians, it's not necessarily taken very positively what I'm saying, because for a whole variety of reasons. But in the field of art, there's this kind of level of play that we can have with ideas, which gives me a lot of joy to be able to think sort of freely like this. And so one of the things we're doing is we're actually going to be making a mathematics textbook, a very short one, but we're going to have it published initially through art publishers, and then hopefully eventually try and get it into curriculum where we can and things like this. So we're working on a kind of accessible high school level book with like a lot of graphic design and history and things like this. But it's kind of a long-term project, I think, basically out of the absence of what you're asking for. But if anybody here has text that they'd like to recommend, I'd love to hear it too. And thanks for your question.
Yeah, and just we have one more question in the chat, and just to add to that, just for a moment too, Byron, I'm just thinking too about you as an artist. We got to see a glimpse of some of your video work, but sort of thinking about what kind of story or visual narrative, you most want to tell or count, right, as an artist, especially working in digital media. So, I love that idea of telling narratives and stories behind numbers, right, and giving them a different kind of life. So, fascinating to hear more too about your own art and sort of how math is informing it, or what you want to say about math, right, through your work. Okay, we've got a question here from Nathan. I think we'll have a couple more minutes. So Byron, can you say more about your concept of infinity and maybe how it relates to your critique of expansion, growth, and colonialism? I was inspired by Badiou's attempt to set theory to provide a rigorous proof of infinity against finitude, or against the closure of the world. But is this rationalist, or is it rationalist expansion? Good question.
Wow, that's a heavy hitter. Thank you, Nate. That's great. So, against finitude.
That's a heavy one to end on too, but it's
no, it's really good. It's just worthy question. Of a little bit of a pause here. I think there's a bunch of interest. I mean, I guess maybe I'll speak a little bit more generally about Badiou than to go into the idea of a rigorous proof of infinity, because that's so much in that question. I mean, first of all, I think one of the things that I find kind of comforting in mathematics is the multiplicity of infinities, that there are many different sizes of it, even though it's all forever. So that, as shown by Georg Cantor, which would be the original person who explained that. So that, for me, in a sense, gives me kind of comfort to know that there is this, expanse of different infinities. And I'm not sure that once we're kind of there, rigorous proof of infinity against finitude or against the closure of the world. Is it rationalist or rationalist expansion? Okay, I'll just kind of end on one kind of counter argument, which is there's this group called the intuitionists. And the intuitionists believe that there's no need for infinity, but rather they're actually quite involved with like Einstein's theory and things like this. But what they are trying to say, and I'm not going to explain how, but they'll say that we don't need infinity because once numbers go on so long, like what good are they anyway? We might as well just cut it off. But what that actually allows them to do is to say that multiple things can exist at the same time. And so there's this sort of thing where they're like, there's no infinity, it doesn't matter, but now we can have multiple things that are different happening at the same time. Sort of what I was saying about addition and subtraction, you could have them happening at the same time, even though they're different. There's something called intuitionist mathematics, where you don't even need infinity, and you can start having multiple operations simultaneously. So, and I find that I'm kind of against it because I want the world to be infinite. There's something very, like I was saying, comforting about that. But at the same time, I'm also comforted by the idea that many things could be true at the same time. And they actually need to get rid of infinity to be able to do that. So sorry for not answering your question so explicitly, but I'll leave it there with the intuitionist approach.
It's a valiant effort too, and in 2 minutes, Byron. So thank you for that. It says a great answer. So thanks. Thank you, Byron. I think we are now right out of time. We're 2 minutes past, but just thank you so much for presenting as part of the speaker series. This was a fascinating talk, really engaging, and for someone who hasn't been in a math class since grade 12, this made me excited again about math. So thank you. You brought it alive for us. So thank you so much for sharing your thoughts. It was a really fascinating talk today. So thanks, Byron.